circuit. I'll be writing the values of different components here. So for this circuit now, VDD is 25 volt. Let's take VDD as 25 volt. We'll solve this problem. Value of RD is, let's say, 4.7 kilo ohm. 4.7 kilo ohm. Okay. Then R1 is 40 mega ohm. Okay. R1 is 40 mega ohm. Then R2 is 10 mega ohm. Mega ohm. Okay, and we are giving the signal. We are giving the signal through a resistance of 2.2K. You please draw this diagram, 2.2K, and here I have connected my input signal source. Okay, I'm using this DC ground, and there is no R in this case. Okay, RS is not there, so I have shorted this. RS is upstream in this figure. There is no RS. So RD is 4.7K, R1 is 40 mega ohm, R2 is 10 mega ohm. What we have to do for this circuit? See, threshold voltage is also given. Value of threshold voltage, VT, is equal to 3 volt. You know what is threshold voltage? That is minimum gate to source voltage required to form inversion layer. Then conduction parameter K is also given as 0.4 milliampere per volt square. Okay, what you have to find? You have to find VGS, VDS and ID, or I will say in short, find the operating point. Okay. VGS, then VDS, VDS and ID. Okay, threshold voltage is given to you. Okay, so how to start the problem? See, for first thing, VGS can be easily find it out. Okay, but now you have to find the operating point. Okay, so it is the thing that you are doing DC analysis. Okay, while doing DC analysis. Okay, so when I say that I have to do DC analysis or AC analysis, some things you must remember what to do with the power sources and the capacitor. Now it is not mentioned that you have to do DC analysis. So even though you do not perform these operation, you start the problem directly, you will understand it. Okay, but if the same question is asked like perform the DC analysis of this circuit, what you are supposed to do? So now DC means, okay, are you getting? I am telling you this problem in two ways. Either it can appear as perform DC analysis of this circuit, or simply find VGS, VDS and ID. In second case, even you don't do the other thing, it is going to work. But this is same as the DC analysis. And what you will do when you want to do DC analysis, it means there must be only DC signal present in the circuit. Now, what about the input capacitor? You are giving input signal. Okay, you are giving input signal from this point through the capacitor. Now, when it is the question for DC analysis only, does this capacitor passes DC? Does the capacitor passes DC signal?
No.
No, because no, the reactance offered by a capacitor Xc is equal to 1 upon 2 pi Fc, right? Where F is the frequency of the signal and for DC this frequency is 0. So this Xc will become infinite for the DC signal and therefore it is act like an open circuit. So it will not allow to pass any DC signal. So this circuit is considered as open circuit. So I have to replace this capacitor by open circuit. So when I replace this capacitor by open circuit in DC analysis, this rest of the parts will be disconnected automatically. Hello?
Like,
Piyush, please mute yourself. So rest of the part will be disconnected because I have opened. Are you getting this? I have opened this, so the rest of the part is disconnected. And here also I am going to open this, so this circuit will be like this. So there is only this point. Now this capacitor is open circuited. Let me also tell you that many times you will find here the resistance and along with the capacitor. So in that time, if you open this, this resistance will come into picture. Okay? This case I will discuss separately. Got it? What to do for a DC analysis, and whatever is the AC source, when you are opening this capacitor, so these things will get disconnected. Okay, and yeah, if any AC source you have to ground it, but right now you have to ground. Right now, when you have opened this capacitor, this portion is disconnected. Okay, further. Now let us solve the problem. Find VGS. Okay. How to find VGS now? Where is your VGS? Here it is VGS. Between, this is your gate terminal and this is your source terminal. So between these two, you have VGS. You have VGS. Even you start your problem directly, there is no problem if unless and until it is given DC analysis. You know, you understand, you have to consider only DC. So you have to find VGS. So what is VGS? VGS is the voltage between these 2 points. Now there is no resistance here. RS is not there. So whatever is voltage present across R2, that same voltage is there. What is VGS? Is the voltage between this point. VGS is the voltage between this point and this point. Now this is also ground and this is also ground. And moreover, there is nothing. So your VGS is nothing but VG. Your VGS is nothing but the gate voltage, means gate to ground. VGS is nothing but VG. Now last time we have finded it. So what is this voltage? This is the voltage across resistance R2. Okay, so I will write this as I into R2. VGS is the voltage between this terminal and this point, ground. What is there in between two? There is a resistance. So voltage drop across this resistance. Now you see this is not there. Okay, this is not there. So VGS is the voltage across R2. R2 is there, okay? Otherwise you will get confused. After removing this portion, when you open the capacitor, this much portion is disconnected. So R2 is there. So now what is the current flowing through this branch? Yes, last time we have done this. Please tell me. The current which is flowing through R1, same current is flowing through R2, because you know gate current IG is 0. This current is 0, right? Therefore, the current which is flowing, I we have calculated. What is I equal to? If you apply KVL in this loop, you will get I. So I is equal to VDD upon, in the last derivation, we wrote it R1 plus R2. What is your VDD? It is 25 volt. 25 volt divided by R1 plus R2. So what is R1 plus R2? 40 mega ohm plus 10 mega ohm. So it will be 40 plus 10. It is in mega ohm. Okay. Mega ohm. So it will give you, if you solve, it will give you
0.5.
0.5. Now what is what I will do? I will continue here. This is your I. Now what I want? VGS. VGS is equal to I into R2. I into R2, that is equal to 25 volt upon 50 mega ohm multiplied by what is value of R2? 10 mega ohm. Okay. So this mega ohm will get cancelled. This was your 0.5, 0.5 into 10, it will be 5 volt. Correct? Yeah, it is. I write here only 5 volt. So I got VGS equal to 5 volt. Understand? So first part of operating point I have done, I have find it VGS. Now what I have to find? VDS. Okay, I'll move little fast now. Now I have to find VDS. So VDS is present in this loop. So I have to apply KVL over here. So if you apply KVL, what the equation will be? It will be VDD equal to IDRD plus VDS. Where is your VDS? Here is VDS. Here there is VDS. So what you will get? VDD equal to IDRD plus VDS. Now there is no RS, so there will be no term ISRS. Okay. But now to find VDS, you need ID. So how to calculate ID? I told you. Let's make some assumption. What is that assumption? Let MOSFET is in saturation. So whenever you are solving the problem of MOSFET, you need ID. So you can assume that MOSFET is present in the saturation. Therefore, we consider value of ID is equal to K times VGS minus VT bracket square. Then we will find VDS and then we will verify whether MOSFET is actually present in saturation or not. Okay. So let MOSFET. Are you getting this point?
Yes, ma'am.
Yes, ma'am.
Because I have to take some value of ID. Okay. So ID, there are two types of ID in the MOSFET. Either MOSFET will be in saturation or it will be non-saturation. So what we will do, we will consider MOSFET is in the saturation region. Therefore, I can take value of ID as, therefore I'll take ID is equal to K times VGS minus VT bracket square. Okay. What is value of K? 0.4 milliampere per volt square. So I'll write here. It is 0.4 as it's milliampere. So I'll take into 10 raised to minus 3. What is VGS? We have calculated VGS as 5 volt. And what is VT given is 3. So minus 3 volt bracket square. So if you solve it, how much does it comes? This will be 2 volt square. So 2 volt square will be 4 volt. So it will go 1.6 into 10 raised to 3. So it will be 1.6 milliampere. 1.6 milliampere. Are you getting? 1.6 milliampere. You have to keep your calculator with you. Okay, so you have find it. So second thing, you have find it VDS, you have find it ID. But right now, I don't know whether my ID is correct because I assume it is in the saturation. So with that assumption, I got correct ID. Okay? Now with this assumption, let us find VDS. How to find VDS? Apply KVL in the output circuit. To find VDS, apply KVL in output circuit. What it will give? Sanga mala. Start from this to ground. So you get VDD minus IDRD minus VDS equal to 0. Can you see? You can zoom your screen. Okay, from this, I will put value of what is VDD? It is 25 volt. ID we are calculated as 1.6 milliampere. RD value is 4.7 K. So from this, you will get VDS. So VDS is equal to VDD, that is 25 volt minus 1.6 into 10 raised to minus 3 into value of RD, that is 4.7K. This is 4.7. So you get value of VDS equal to, I got it as 17.48 volt. Okay. So both the things you have find it. Now tell me how to confirm that your assumption is correct. What to do? We have seen last time. How to check whether assumption is correct. By assuming that MOSFET is present in the saturation, we have calculated the things. Now we must ensure that our assumption is correct or not. So how you will check? Yes, anybody, do you remember? Do you remember? Let's check if MOSFET is in saturation region. How to check?
VDS is greater than VDS in saturation.
So you know this is the characteristics of MOSFET. From this point, MOSFET enter into saturation region. Okay, and the value of this on this axis we used to show VDS, on this axis we used to show ID. So when value of VDS exceeds VDS sat, this value is VDS sat. And now what is VDS sat? This is equal to VGS minus VT. VDS sat is equal to get to source voltage VGS minus threshold voltage VT. Okay, if the present value of VDS is greater than calculated value of VDS sat, then your MOSFET is present in saturation. So now let us calculate VDS sat. VDS sat comes to be, what is your VGS? 5 volt. And what is your VT? 3 volt. So VDS sat comes to be 2 volt. And what is your actual VDS? Actual VDS is 17.4.
17.4.
Okay. So actual VDS 17.48 volt is greater than 2 volt. Okay. Therefore, your assumption is correct. Assumption is correct. Got it? So this way, you have to solve the problem based on DC analysis of the MOSFET. You have to find operating point. One more thing, let me tell you. I'll share a whiteboard with you. Once you find, now you please tell me the value of operating VDS and ID. This is my y-axis where I used to show drain current ID in milliampere. Okay, and this is my x-axis where I used to show VDS in volts. Okay, now we suppose this problem is extended to suppose I want to extend this problem as draw the DC load line for same. Okay, and find operating point. Are you getting? I want to extend this problem as draw DC load line for this circuit and find the operating point. काय मी म्हणणार आहे की मला DC load line find करायची आहे सर्किट साठी आणि operating point. So out of that you have finded operating point. Now how to find DC load line? That you know. DC load line is the line which is connecting the maximum value of VDS and maximum value of ID. So how you will find maximum value of VDS and ID? If you apply KVL at the output loop, now you have the screenshot of circuit. Apply KVL at output circuit. So what we have already done this. When I shared the new thing, have you taken the screenshot? Let me try. Moment I clicked off annotation, the problem was gone. Okay, no issue. We have done. It is there in the. You understood how I solved the problem?
Yes, ma'am.
Yes, ma'am.
So we have find it. We will apply KVL at loop. What we have find it Q point. In that Q point we have find it Q point, operating point. That is, we got VGS equal to, how much was VGS? 5 volt, I think. Yeah, VGS was, we
Yes, ma'am.
find it VGS equal to 5 volt. We got VDS equal to 17.48
17.4.
volt, and we got ID equal to 1.6 milliampere,
1.2.
right? So we have finded this operating point. Now, if somebody asks you, draw the DC load line and find the operating point, then how to do? Simply apply KVL in the output loop. If you apply KVL in the output loop, you will get VDD minus IDRD minus VDS equal to 0, because there is no RS in the circuit, right? Now you know what to do in this. Let's call this as equation equal to 1. I will not arrange it in the form of y equal to mx plus c, because now you know what is DC load line. So let us make first ID equal to 0. So in that case, you will get VDS max. Okay, you will get VDS max. So if you put ID equal to 0, what it will be? VDS equal to VDD. Okay. And if you substitute VDS, put VDS equal to 0, so you will get ID max. Therefore, you get whatever ID you will get, that will be maximum. So I will write ID max is equal to what it will be? VDD upon RD. VDD upon RD. So VDS max is equal to VDD. And how much is VDD? 25 volt, correct? That is equal to 25 volts. So you will get maximum value of VDS max is 25 volt, and ID max, you please find it out. It will be 25 volt divided by RD is 4.7 K.
5.2.
Okay, 5.2.
2.
Yeah, 5.3 I got milliampere. Okay, it is equal to 5.3, because this is K, it will go as -3, it will milliampere. So you got these two things. So let us show this ID max on ID axis. So I will mark here as 5.3. This is value of ID max, means in my circuit, whatever circuit we have drawn, I can get maximum current as 5.3 milliampere, and I can get maximum value of VDS as 25 volt. Okay, so these are the two maximum possible values. Now let's join these 2 points, and this becomes your DC load line. Okay, what is this? Is it not easy? This is DC load line. Okay? This is DC load line. Now you know that your operating point will be there on the DC load line. Okay. More or now you have to show it. What is value of VDS you are getting? 17.48. So if this is 25, it may be this is set origin. This will be 12.5. Middle part will be 12.5. So your 17.48 will be somewhere here. Okay. 17.48 volt. And your ID is 1.6. If this is 5, so something let's say 0.5. So I will draw this is the point where it is intersecting. Let me take my difficult. This is 1.6, let's say 1.6 milliampere. This is 5. If you take a proper scale, you will get it properly. Here I will write 25 volt. So the point on the line where both intersect, this point is called as Q point. This is the location of your Q point. Got it? How to find? More if you want to draw the curve, this curve will be for VGS equal to, because you got VGS 5 volt. So this curve is for 5 volt. On this curve, what is value of VGS? VGS is equal to 5 volt. So whenever somebody asks you to find draw DC load line, simply apply KVL in the output loop. Find the expression for ID and VDS by keeping find ID by keeping VDS 0, find VDS by keeping ID 0. You get 2 points that are the maximum value of ID and VDS. Show this points on the graph, join this line, this is a DC load line, and whatever operating point you have already find it, that is the existing value of ID and VDS you show on that graph, and that will be your operating point. So this is how you have to draw DC load line and operating point. Understood? Yes? Yes or no? Any doubt?
Yes, ma'am.
Yes, ma'am.
Everybody, if you have any doubt,
Yes,
you
ma'am.
can ask me. Okay. You have AC analysis in this circuit also. For AC analysis, will be okay. AC analysis, we will do the things later. So DC analysis of the circuit we have completed. Let us move to an important factor: non-ideal VA non-ideal characteristics of MOSFET. Can you see my screen? Can you see non-ideal MOSFET
Yes,
characteristics?
ma'am.
Today, yeah, today
Yes,
we
ma'am.
will. Yeah, thank you. So today we'll extend little by 5 minutes only, because initially we have discussed the things. So let me complete at least 2 definitions of this. And from exam point of view, mark this as very, very important. Okay, please mark this as very, very important. You will definitely file the question based on non-ideal characteristics of MOSFET. So there are different non-ideal characteristics of MOSFET. Generally, definition is asked. Every definition for 2 marks. You have to explain it properly. So what are its non-ideal characteristics? These are finite output resistance, body effect, subthreshold conduction, breakdown effects, and temperature effect. Got it? These are the five main non-ideal characteristics of MOSFET that we have to explain. Now let us talk. I will first explain you the body effect because it will help me to complete two parameters in the remaining part of this lecture. Okay, so let's talk about body effect. You have seen the construction of MOSFET. Okay, you have seen construction of MOSFET, and you know that you when you construct single MOSFET. Everybody, are you there? Have you marked your attendance? Please unmute yourself once. Let me know you are there.
Yes, ma'am.
Yes,
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
yes. Okay.
Yes, ma'am.
Unmute yourself
Yes,
now.
ma'am.
Good. So when I come to know you are there at the next team, so I feel very good. Okay. So we have seen the construction of MOSFET that first of all we have some substrate. Within that substrate, then we have the source and the drain. We have the source and the drain. And there is some gate also. And above this, there is SiO2 layer as well. Okay, these things you know. Now, whatever we have seen is construction of a single MOSFET. Now, I will not draw it again. You know, this is gate, these terminals which are taken out, that will be drain and source, and up there will be body terminal. Okay, and we always connect that body terminal with the substrate. So, if this is my substrate, this is the substrate, and there is the body terminal. Okay, and it is connected. Forget about the symbol. It is connected, right? This is gate and this is drain. This is gate, this is drain, this is source, and this is substrate of the body. So substrate and source, they are always connected together. It means they are at same potential. Clear? Substrate and source, they are at same potential. Now, when the MOSFET ICs are formed, so see, in VLSI technology, in chip, there are hundreds, not hundred, I'll say thousands of elements are connected together. Okay. Now, in the cases when you, in that cases when you want to form multiple MOSFET, okay, so there will be a common substrate, and inside that substrate, now in the next unit you will come to know about CMOS, complementary MOS. So there you will be finding such type of structure. Okay, so when there are multiple MOSFETs connected together, what happens? See how these MOSFETs will be made. So this is the N block and N block. Substrate is P substrate, common for all. So this is your first MOSFET build. This is the first MOSFET build. So you have a source, you have a drain, and you have a gate. Clear? Can you see properly? I have enclosed it in the blue color rectangle. You have a source, you have a drain, and you have a gate. This is MOSFET number one. When second MOSFET is fabricated, this portion is common for the next. So I draw it different color, let's say. Now for the second MOSFET, this drain of first MOSFET act as the source of second. So multiple MOSFETs are connected in series. कसं कनेक्शन केलंय बघा. पहिल्याचा ड्रेन हा सेकंड मॉस्फेटचा सोर्स झालेला आहे. Then there is a gate and there is a drain. Now if you see structure combinedly, this is one source, this is one drain. Okay, and further what we'll do, we'll be connecting both get together in series. So when the multiple MOSFETs are formed into series, what happened? The drain of first MOSFET becomes the source of another MOSFET. Now, you know, when we see a single MOSFET, we used to connect source with the substrate, source with the body. Okay. So if I connect this source with the substrate, it will be this source and substrate, and these are at ground potential. Okay. Remember, try to understand my point. We are connecting the source of first MOSFET to the substrate. This is how we are going to connect. The source of first MOSFET, we are about to connect it to the substrate. So this junction, the source and substrate, so there is some junction, no? So this junction, right now we have connected it to ground potential. But when you think of MOSFET number 2, the source of MOSFET number 2 is nothing but the drain of MOSFET number 1. And here, as a common structure, here you are going to take the output. So now, can I connect it to ground potential? No, because I have connected multiple MOSFETs in series. The drain of first and source of second, they are same. Therefore, I cannot make this terminal at the ground potential. म्हणजे काय झालंय की पहिल्या मॉसफेटचा सोर्स आणि सबस्ट्रेट हा एका वेगळ्या पोटेन्शियलला आहे आणि दुसऱ्या मॉसफेटचा सोर्स आणि कॉमन सबस्ट्रेट हा दुसऱ्या पोटेन्शियलला आहे. अंडरस्टूड? Because I cannot ground it now. I cannot connect it. I cannot ground it. हा सोर्स हा एक सोर्स झाला, तो सोर्स मी सबस्ट्रेटशी कनेक्ट केला. But because of this, what is happening? This junction is at different potential and this source substrate junction is at different potential. Are you getting my point? When you form number of MOSFET connected together inside IC, the source of first MOSFET is connected to the substrate and that can be connected to the ground. But you cannot connect the source of second MOSFET to the substrate because source of second MOSFET is the drain of the second one, the drain of the first one. So that is why you cannot make it connected to the substrate at a ground potential, कारण हा तुमचा output terminal झाला आता. बरोबर? Are you getting?
Yes,
Please let me know. So because of this, what happens? The source substrate junction of MOSFET 1 is at different potential and source substrate junction of MOSFET 2 is at different potential. Now, if you remember, we have defined one parameter called as VT, threshold voltage. What is that? Somebody please tell me what is VT, threshold voltage? Shubham Shrisat, why you are so late? Okay, somebody tell me what is threshold voltage? Forgot it? Please do it fast, guys. What is threshold voltage? How can you forget?
The minimum value of voltage to carry drain current.
Very good. The minimum value of get to source voltage required for establishment of virtual channel or required for conduction of current through the MOSFET. Okay. And if you remember, because of the channel gets established because of that sufficient value of threshold voltage, VGS, that is, we call it as threshold voltage. So now for this MOSFET, when I connect this source and this substrate together, whatever value of voltage required to form a channel, I call it, let us say, VT1. Now, if you talk about this MOSFET, will your VT1 remain same? Let's call this voltage as VT2. So what do you think? Will the VT1 will remain same as, will that VT2 will remain same as VT1? Same राहील का? In this case, your source and substrate was ground potential. Okay. But in second case, your source and substrate, it is not on the ground potential. It is having different potential. So the voltage which is required to establish the to form inversion layer will be different than that, because source and substrate here, they are at different potential. Here they are at some different potential. So the value of VGS required to create inversion layer, or I will say simply, the threshold voltage for this MOSFET is not same as threshold voltage for this MOSFET. Okay. And this effect is called as body effect. The change in the source substrate junction voltage change the threshold voltage. काय झालं आहे? In the first case, when you find Vt, your source and substrate are at same potential. But in second case, they are not at same potential, they are different potential. Therefore, this Vt1 will be different from this Vt2 actually. And this change in the threshold voltage, why this change is happening? Because of change in the source substrate junction voltage. Source आणि substrate या junction मधलं voltage जे आहे जे potential आहे, that is different for both MOSFET. Therefore, there is variation in their threshold voltage. You got my point? This effect is called as body effect. काय म्हणतात त्याला? Body effect. Because source and the body, they are at different potential for different MOSFET. Therefore, there is variation in the threshold. This effect is called as body effect. Understood? Can anybody define it in one sentence? It is there written in front of you. Just try to define. Try to define the body effect. Come on, let it be wrong, don't worry. Step by step also you can explain. Yes. Please unmute yourself. Haven't you? Shall I repeat it? Shall I repeat?
Yes, ma'am.
Yes, ma'am.
Yeah. So, when we consider, now listen, I will repeat in step by step. When we consider single MOSFET, in that case, the source and substrate, they are at same potential, at ground potential. Okay. So, in this case, we define threshold voltage as value of VGC required to form the inversion layer, or the value of applied gate to source voltage at which MOSFET will start conducting. Okay. But in actual practice, when there are multiple MOSFETs connected in series, the source substrate junction of first MOSFET is at ground potential, but the source substrate junction of second MOSFET is not at the same potential. Why? Because the drain of first MOSFET acts as a source of second MOSFET. Therefore, we cannot keep this terminal at the ground potential. So, when there are multiple MOSFETs connected in series, there is a variation of source to substrate potential, source to substrate junction potential. And because of these changes, the threshold voltage for every MOSFET is not the same. So, the change in source to substrate junction voltage makes the threshold voltage to vary. This effect is called as body effect. I'll repeat again. I try to explain in Marathi. सोर्स आणि सबस्ट्रेट हे जंक्शन सगळ्या मॉसफेट साठी डिफरंट आहे. For first MOSFET, source and substrate are connected together, that is at ground potential. But for second MOSFET, source is not connected with the substrate because it is the gate drain terminal of the first MOSFET. So it cannot be connected to drain. तिथे तुम्ही आउटपुट घेणार आहात, त्याच्यामुळे तुम्ही त्याला ग्राउंड करू शकत. म्हणून हा जो जंक्शन आहे, हा सबस्ट्रेट आणि हा एन रिजन याच्यामध्ये हा जो जंक्शन आहे, हा जंक्शन, let's say J1, this junction. So with this junction potential, let's say VT1 is the threshold voltage required for this MOSFET to turn on, to make it conducting. But if you see this source and this substrate, this junction J2 is at different potential, कारण हा ग्राउंडला नाही केलेला, त्याच्यामुळे ह्याचं हे जंक्शन पोटेन्शियल वेगळं आहे, हे जंक्शन पोटेन्शियल वेगळं आहे, त्याच्यामुळे the threshold voltage required here and required here, they are different. म्हणजेच source आणि substrate junction potential, different MOSFET, those which are connected in series, that varies Therefore, its threshold voltage also varies. So this change in the threshold voltage, which we get due to change in the source to substrate junction voltage, is called as body effect. लक्षात आलं? कॉन्सेप्ट कळलाय तुम्हाला? Have you understood the concept of this? बॉडी इफेक्ट म्हणजे काय? की जेव्हा मॉसफेट सिरीज मध्ये कनेक्टेड असतात इनसाइड द आयसी, तेव्हा एकाचा ड्रेन हा दुसऱ्याचा सोर्स झालेला असतो. तर या केसमध्ये हा सोर्स तुम्ही सबस्ट्रेट जो की आपण ग्राउंड पोटेन्शियलला कनेक्ट केलेला आहे पहिल्या सोर्स सोबत, त्याच्यामुळे पहिला सोर्स आणि सबस्ट्रेट हे पोटेन्शियल वेगळं आहे, हे जंक्शन पोटेन्शियल वेगळं आहे, आणि दुसरं सोर्स आणि सबस्ट्रेट हे जंक्शन पोटेन्शियल वेगळं आहे. इथं आपण ग्राउंड केलेलं नाही, त्याच्यामुळे दोघांनाही वेगवेगळं थ्रेशोल्ड व्होल्टेज लागतं. So this variation in the threshold voltage due to variation in the junction potential is called as body effect. Is it clear? लक्षात आलंय का?
Yes, ma'am.
Yes, ma'am.
एवढं लक्षात ठेवा की जो VT आहे threshold voltage that is different for this MOSFET and this MOSFET. हा का डिफरंट आहे? कारण ह्याचं सोर्स टू सबस्ट्रेट जंक्शन व्होल्टेज वेगळं आहे आणि ह्याचं सोर्स टू सबस्ट्रेट जंक्शन वेगळं आहे. का वेगळं आहे? कारण हे दोघं तुम्ही एकत्र कनेक्ट करून ग्राउंड केले, पण हे दोघं तुम्ही एकत्र कनेक्ट करून ग्राउंड करू शकत नाही, बिकॉज दिस इज ऍक्टिंग ऍज अ आउटपुट टर्मिनल ऑफ दिस कंबाईन स्ट्रक्चर. एवढं लक्षात ठेवा. सो दिस इफेक्ट इज कॉल्ड एज बॉडी इफेक्ट. व्हेरी इम्पॉर्टंट डेफिनेशन. ओके, नेक्स्ट विल सी. Next, this I will take subthreshold conduction. Subthreshold conduction. Now, initially we have defined threshold voltage. Everybody know it now. What is threshold voltage? Threshold voltage is the value of VGS required to create inversion channel, or in other way, I will say required for a MOSFET to start conducting. बरोबर? Now what happens for every MOSFET, that this is specified in the data sheet. You try to download some data sheet for a MOSFET. Okay, in practical I'll show you. So for every MOSFET there is value of VT is given to you. Okay, value of VT is given to you. That this, let's say VT is 3 volt. It means when you apply value of VGS equal to 3 volt, then only your MOSFET will start conducting, and before that, for any value less than 3 volt, MOSFET will not start conducting. Got it? This is the meaning. But actually what happens, whatever is the value of VT, sometimes your MOSFET start conducting before this value itself. Or there is a very small change. I will try to show in this characteristic. Now this is I versus VGS. This is gate to source voltage, and this is drain current. If I want to plot this characteristic by this under root written, I will let you know. So we know that, look at this red color graph. From 0 to VTN, this is threshold voltage, there is no current. So that is why I am showing it on this axis. And from VTN onwards, the current starts flow. It increases linearly with VGS. पुढे जसं VGS वाढणार तसं तुमचा करंट वाढणार आहे. But in fact, when you see, actually the conduction is like this. It is not 0 up to threshold, but before threshold voltage it start conducting from this point. Okay, so conduction, current conduction of MOSFET below the value of VTN, this is called as subthreshold. Subthreshold, before threshold. Okay, so in practice what you observe, that MOSFET start conducting means current is very low. Okay, this current is very low, of course, but still there is a very small current that flows even before the value of threshold voltage. लक्षात घ्या, MOSFET current conduction कधी start करतो? Actually it starts from VT, but in practice you will find that a very very small value of current is flowing through the MOSFET before the threshold voltage. Okay, so now you understand, when there is only one MOSFET there is no problem. Okay, we can ignore this current. This current is very very small. But I told you in the previous slide that in VLSI technology, you are having thousands of MOSFET. You have multiple MOSFETs connected together. Now, suppose if you are connecting multiple MOSFETs together in series, so these small current will get added, right? Are you getting? Every MOSFET start conducting by a very small current is flowing through the MOSFET even when VGS is less than VT. Okay, but this current is very small and can be ignored. But when there comes a question that you are connecting multiple MOSFET together, this small current will get added, and the current which is flowing will be sufficiently higher. And when such current flows, significant power dissipation takes place. Okay, even though that MOSFETs are not conducting, significant power dissipation may take place in non-conduction of more number of MOSFETs on IC. This is called as subthreshold conduction. Subthreshold conduction म्हणजे काय? VGS ची व्हॅल्यू VT पेक्षा थोडी कमी असताना सुद्धा MOSFET मध्ये करंट फ्लो होतो and that current is negligible. Okay, this is called as subthreshold conduction. Okay, but when there are number of MOSFETs connected in series together in an IC, these small current, as an addition of all these currents, the current is higher, and therefore these current dissipate power in the MOSFET even the MOSFET is not conducting. कारण VGS आल्यानंतरच MOSFET तुमचा प्रॉपर कंडक्शन सुरू करणार आहे, पण त्याच्या आधी MOSFET मधनं व्हेरी स्मॉल करंट फ्लो होत आहे. तर एका MOSFET साठी काही प्रॉब्लेम आहे, बट when there are multiple MOSFETs connected together, the small currents are contributing to significant power dissipation in the MOSFET. Okay, so that is a problem. Okay, so what is subthreshold conduction? Flow of very small negligible current in the MOSFET for the value of VGS less than VT. So actually ideal curve तुम्हाला असा मिळाला पाहिजे इथपर्यंत 0. You must get 0 till this time and then linear increase, but practically you get some increase from the value before VT. Now what is this thing? ID equal to K times VGS minus VT bracket square. You know this is the current equation for the MOSFET when MOSFET is in the saturation region. Take square at both the side, so this will go, and ID, this is shown now. ID is a linear function of VGS because you know ID is going to vary with VGS. So as VGS increases, ID increases linearly. So that is trying to show here. So you just plot the curve when it is ideally, and this is what experimental actual curve that you get. लक्षात आले हे दोन पॅरामीटर? Yes or no?
Yes, ma'am.
Two non-ideal parameter we learned today. One is